So my name is Yilun Zhang. So I'm the co-founder and CTO of NKN Labs. So today I'm going to talk about the technical solutions to achieve million node consensus and more than 10K TPS with pure BFT-like algorithm. So first of all, let's take a look at the scalability. So what do we mean by scalability? So there are two typical meanings when we talk about scalability in blockchain. So the first one is a transaction per second, that is the throughput of the blockchain. And the second one is the network size. So the network size is some sort of like developed part. And it actually very important because it affects how decentralized the blockchain is, and it determines how robust the blockchain is, and how easy it can be attacked, the security part. And in some blockchains, such as NKN, which provides a off-chain data transmission network, it determines the aggregated output throughput of the whole network. So it is very important for blockchain to be able to scale to a large amount of network size in order to be reasonable in those properties. But if we look at the throughput and the network size for most blockchain and even like the DEG-based system, we found that there is a throughput and network size trade-off. Basically, the larger network size is, the blockchain is, then the smaller the TPS would be. So we will soon see that what's the reason behind this. But at NKN, we are essentially like a data transmission network, so we want a large amount of nodes in the network. So that's a requirement, and also we need high throughput. So we really want to push the line towards the upper right corner. So let's take a look at how we try to achieve that. So first of all, if we look back into the graph, we will see that there are two groups of dots on the graph. So the red group is POW based, and the purple group is BFT-like consensus. So typically we will see that the BFT-based algorithm has higher TPS, and that's actually one of the reasons why we choose a BFT-like consensus algorithm. So it has a few advantages, such as near instant finality instead of event consistency. It's energy efficient, of course, and typically it has less proposal per run, such that it has a higher aggregated throughput in terms of the TPS. But it also has a few drawbacks. So for example, the BFT-like consensus is known for not scalable in terms of the network size. And also it has some security concern compared to the POW. So the biggest problem in the BFT algorithm is the scalability in network size. So the reason why BFT is not scalable is actually in the network part. So if we consider that the standard practical BFT algorithm with n fully connected consensus node, then for each run or election, every node needs to send a message to every other node in the system, so that each node will send and receive OM message per block. And every node needs to maintain n-1, almost n connections to the other nodes, which is not acceptable when n is large, for example, a few hundred or probably 1,000. So we can see that the bottleneck in the BFT-like consensus algorithm is actually the OM message complexity per node when doing the consensus. So there are typically two straightforward ways to make it more scalable. So the first one is reduce the n. So it's essentially elect a smaller group of consensus nodes efficiently per run and do a BFT among them. And the second possibility is reducing the message complexity OM. So instead of having to communicate with all other nodes in the system, each node only communicates with a smaller group of other nodes in the network. And this is a solution we choose. So our consensus algorithm is actually inspired by Cellular Automata. So Cellular Automata is a network of a state machine where each node updates its own status based on its local neighbor's status and according to some like predetermined rules. So one interesting part, so there are a bunch of stories to tell about CA, but we probably don't have time. But the one interesting property and important property of the CA is that it, even though each node only gathers local information and has a local interaction, there would be global collective behavior emerge from those local interaction. And global consensus is a special case where all nodes end up with the same state. So that's actually how our name comes from. The NKN stands for New Kind of Network, and the name is actually inspired by Stephen Wolfram's New Kind of Science term. And by the way, Stephen Wolfram is who is a legend and also joins NKN recently as a technical advisor. So, inspired by the Cellular Automata, we proposed a scalable consensus algorithm called the majority vote Cellular Automata, and in short for MOCA. So the algorithm has a bunch of details, but let me tell you something, some very high-level description to the consensus algorithm itself. So basically, each node selects a random set of neighbors among all the nodes in the network. And for a proposal, for example, a block to vote, each node sends out his initial vote, whether he wants to accept or reject the block to his neighbors. And each node listens for his neighbor's vote. Whenever he sees that the majority of his neighbors having a different vote than his own state, then he changes his own vote and sends a new vote to his neighbors. And the algorithm runs continuously at the third step. So one important thing in the algorithm is how to select the random neighbors. So the neighbors should be randomly chosen to make it to make the convergence faster. And also the choice of neighbors should be verifiable or verifiable in order for the malicious node to not be able to select like other honest node or like excluders by unintention. And also we want the topology to be sparse so that each node has a relatively small amount of neighbors in order to make the network to be scalable. So our choice is that each node randomly generate a verifiable node ID. And the overall topology is based on the core DHT topology, such that it's verifiable and scalable. So that we have all the property, and for the scalability, each node only has around like O log n neighbors, such that it's a quite small amount. So we can show that both theoretically and numerically that the consensus algorithm converge quite fast to the consensus state in just a few steps, even though the network initially stands at like 50-50 state, that is half of the node have the agree state and half the rest have the reject. And we can see that the more neighbors we have in the network each node has, the faster it converges. So to analyze the scalability of the MOCA consensus, we look at the message complexity per node. So because each node only has O log n neighbors, that means for each block, each node only needs to send and receive O log n messages, which makes it horizontal scalable. So it can reach global consensus for the whole network size for almost any size in just a few seconds, because for each vote you just send a message to a neighbor, which takes a few like milliseconds to do it. So actually this has been tested, implemented and tested in our permissionless public testnet, which has up to 6,000 nodes and most of them running by community, with almost zero resource consumption in order to perform consensus. So here the resource means CPU, the RAM, and the network. So although the current size is like around like 4K, in order to reach from that point, in order to reach 1 million nodes, each node only needs 67% more resource consumption, which is still nothing. And in order to reach 1 billion node consensus, each node only needs to consume like 25% more resources, which is still nothing. So when we say median node consensus, we're actually quite conservative here. So the one thing we have to face it is that we cannot gain anything for nothing. So so we ask the question, what do we treat the scalability for? So if we analyze carefully, we will see that to see this question, we need to add an additional axis into the fault-tolerant analysis. So traditionally, when we talk about whether a system is presenting fault-tolerant or not, we only care about how many malicious nodes are there in the system, or ratio of malicious nodes. But now we need to add another dimension, that is, let's say for an honest node, what would be the initial state? Like either a high initial state, or like most of the nodes are in the accept state, while the rest, just a small amount, are in the reject state. So when we have this two-dimensional plot, we can see that traditionally the BFT algorithm only cares about the ratio of malicious nodes. So basically, as long as there were less than 1/3 malicious nodes in all this region, then the system would be in the BFT state. But now, the MOCA consensus, the network needs to be in not a tight state. So that means we need to in these two regions. So if the honest node initially has a tight initial state, then the malicious node will be able to pretend to change its vote not according to rule in order to make the honest node not be able to converge fastly. So basically, we call this conditional BFT. So basically, that means whether a system is BFT or not only depends on the malicious node ratio, but also depends on the initial state. But luckily, this can be largely overcome by other part of the system design. So, but we probably don't have time to talk about this. So we mostly talk about the consensus algorithm itself before, but as a blockchain, we also need to have the rule to selecting the block proposer for each round. So this is not the consensus algorithm itself, so we kind of just give an overview. So basically, we use a proof of relay because a background is that NKN is a decentralized data transmission network. So basically, when the data is transmitted in the NKN network, there will be something called signature chains generated. And the signature chain is unpredictable, uncontrollable, but it's verifiable. So that we choose a global best signature chain by some metric as the next block proposer. And we also use verifiable random function to make the signature chain unique in order to prevent some serious attack. So that is for the consensus part. So now we can see that we have pushed the number of nodes to 1 million or more. But what about the throughput? So how can we achieve higher throughput in the blockchain? So there is a very interesting fact that many people are either not aware of or not talk about. That is the bottleneck of the throughput in the public large-scale consensus network is actually not CPU or other resource. It is a bandwidth. So to see why it is true, let's consider the case where we have a certain amount of TPS. And we have n nodes, and each node has m neighbors out of those n nodes. So we use gossip protocol to broadcast transaction, and the transaction should start from a random selected node per transaction. So the result would be each node will receive the TPS times m transaction per second due to gossip redundancy. So there is a redundancy factor m, which is the number of neighbors per node. So typically this redundancy can be reduced if either of the conditions are true. So for example, if the nodes are fully connected, then we can get rid of the gossip protocol, and then we don't have the redundancy here. In another scenario, if the transactions are mostly come from a few nodes out of all the nodes in the network, or we are willing to sacrifice the confirmation time in order to bundle the transaction to a larger block, a bundle, and then we can send the bundle hash first, and then when someone wants the content, he can request it from the neighbors. By doing that, we can achieve, we can get rid of the redundancy. But this is not, so that's why we mentioned transaction redundancy, not the block redundancy, because transaction is small and doesn't apply to the second condition. So sadly, neither condition applies for a large-scale consensus network. So we have to face that in the network phase, we have a large redundancy factor. And even badly, the M is typically O log n in order for the network to have a reasonable broadcast time. So let's now put some realistic numbers. So assuming, assuming we want to achieve 1,000 transactions per second, and we have a neighbor count which is 20, and the average transaction size 25 to 250 bytes, which is pretty small already. Then each node in the network will send and receive 5 megabytes of the transaction data per second, which is possible in lab environment, or let's say, especially when the nodes are sitting together or in the same region in the cloud server. But it's not practical in the public blockchain where nodes are global nodes, and especially some of them are owned by community and your computer running at home. So this is just 1,000 TPS. So if we change it to 10,000 TPS, then each node needs to send and receive 50 megabytes of data per second, which is almost impossible for most nodes currently. So it is worth mentioning that this estimation is regardless of what consensus algorithm is using. It's just based on the simple fact that each transaction needs to be broadcasted to most of the nodes in the network. So in order to solve this problem, we need an efficient broadcast algorithm that can be applied in a large-scale network. So what we did is that we proposed an efficient broadcast algorithm that can achieve exact once or exact k times message sending without compromising latency. Basically, we get rid of that redundancy factor. So the algorithm itself is probably not that easy to describe, but the idea is that we start from the core digit topology, and we can construct the spanning tree starting from any node in the network that can reach out to any other node in the network. So the algorithm itself is a pure local routing algorithm, and there's no additional information or global information needed. So it can reduce the message complexity from the TPS times M to TPS itself. And typically it can boost the TPS by a factor of 10 or more. So for the numbers, if we want to achieve 1,000 TPS, the network, the bandwidth usage is now just 250 kilobytes per second, which is totally achievable. And if we want to reach 10,000 TPS, it becomes 2.5 megabytes per second. It's not trivial, but it's still like much more feasible than before. So as a summary, we talked about two things today. So one is MOCA consensus. It's a conditional BFT consensus algorithm that is horizontal scalable to almost any number of nodes. And the second one is an efficient broadcasting algorithm with optimal throughput and latency. And it can boost TPS by at least a factor of 10 for almost any public large-scale blockchain. And most importantly, everything I talked about today have already been implemented in Go and open source on GitHub, and more importantly, tested with 6,000 global community nodes in our testnet for like several months. And if you're interested, you are welcome to take a look at our GitHub. And yeah, that's it. Thank you for coming.